This is day 15 of coding every day until I hit 1K subs. Today I submitted a Leetcode question I made. I've been wanting to submit a Leetcode question for ages, and I finally came up with one that I thought was perfect. It's called even sum pairs. Basically, you're given an array of integers, and you have to figure out if you can divide all the numbers into pairs where the sum of each pair is even. I'm waiting to see if it will be approved, fingers crossed. I also did my daily Leetcodes. First, largest odd number in string. Spoiler alert if you want to try it yourself. It's an easy one. You are given a large integer as a string. You've got to return the largest valued odd integer, also as a string, that is a substring of the original. If no odd integer exists, return an empty string. A substring is a contiguous sequence of characters. Here's my solution. I converted the string to a list. I check starting at the end, working my way towards the beginning of the list, checking if it's odd, if it's even. Then I remove it using pop, otherwise I return the list converted back into a string. Since it must be the largest odd number, if I get through the whole list and there isn't any odd number, it'll reach the end and just return an empty string. This has a time complexity of big O of n, where n is the length of input string, since we might have to loop over it, and popping an element takes big O of 1, so. Next up, I tackled minimum cost walk-in weighted graph. This one's considered a hard. Big spoiler alert if you want to give it a shot without any hints. The gist is, you're given an undirected graph with vertices, numbered 0 to n1. You've also got a list of edges, where each edge has a start vertex, end vertex, and a weight. The cost of a walk starting at node U and ending at node V is calculated as the bitwise AND of all weights met in the walk. We use bitwise AND, which is just a single ampersand. Given a list of queries, where each query has a start vertex and an end vertex, the task is to find the minimum cost of a walk between them for each query, or return -1 if no such walk is possible. Here's how the solution works. First, we create an adjacency list to represent the graph. Then, the function iterates through each node. If a node hasn't been visited, it calls a helper function to calculate the cost of that connected component using depth-first search. It uses the helper function _get_component_cost. Inside the getComponentCost function, we initialize cost as a number with all the bits set to 1. We start a depth-first search from the given node, and for each edge, we update the component cost by taking bitwise AND of the current cost and weight of that edge. This is done recursively, so we go through all the nodes that are connected. The main function iterates through each query and checks if start and end vertices are in the same component. If they are, we return the calculated cost. If not, we return -1. The time complexity for building the graph is big O of E, where E is the number of edges. Then for queries, it's big O of Q, so overall it's big O of E plus Q. That's it for today. Like and subscribe and comment below what kind of problems you'd like to see me tackle, or any other ideas you have for the series. If you want to help me continue making videos, you can donate at buymeaboba.com, link in description.